Hello everyone, my name is Kasra Ahmedi and I'm a PhD candidate at University of South Florida focusing on security in AI and trustworthy AI. So today in this presentation I'm going to talk about how we can design generic recommender systems. This presentation can be useful in junior level machine learning system design, and you can find some keywords and continue your research and understanding to empower yourself in more technical topics. I'm expected you to know about the basic of machine learning, some concepts like loss functions, gradient descent, training methods, and neural network especially. So that's prettier, but you don't need to know that much information in recommender systems. So let's start. Mostly in these kinds of interviews, you're gonna face some questions like, can you, for example, create a recommender system just like the feed for Instagram or TikTok or X system? So you should recommend the user about the related topics or items that the user may be interested in. Or for example, in YouTube application, there are some videos and you should recommend those videos to those kinds of users. Or we can have that in the Spotify or Airbnb or even at Amazon when you are buying something, those recommenders are in place and they are acting their roles there. So that's really important to follow and learn how those components and systems work. So in these different applications there are different methods and different maybe neural network architecture that may be used, or even maybe there are some situations that there's no neural network in those systems and decision trees maybe work there, but there's some basic understandings that they are shared in all of these applications. So we are going to talk about those concepts in this video. Whenever you face a question in these kinds of interviews or problems, there are some steps that you should follow. The first step is to define the problem and define the objective. So, for example, if you are producing a recommender system, creating a recommender system for YouTube, so what's your goal? So maybe your goal is to having more users click on more items. This can be one goal, or maybe another goal can be increase the watch time of the users. So there are different scenarios and different business idea goals that those ideas can help you to understand how you should design a machine learning model. So prior to anything, just bring yourself into business and just put yourself in that position and say, okay, how can I earn more money? Maybe if my users see more videos, I can earn more money by showing more ads to the users. So that's the objective here. Prior to everything, it's all about business, not about machine learning itself. Then based on those goals, we're gonna do some training. We're gonna create some models there. So every training step needs some data, and we need huge data. There are different kinds of techniques that you can gather data, but you should have in your mind that you need vast amount of data there. And then all of these data create some features, have some features. These features can be numeric or categorical or text or image or video. So you should have a method to understand these features and try to make these features into numbers. That's another thing that you should consider, because at the end, your machine learning model, the only thing that's needed, it's only understand numbers, not images, not videos or text. Everything should be changed to numbers. Then you should go over the modeling and create a robust model. That one important thing in industrial projects and good projects is that the model which is developed should be fine-tuned and have an iterative approach that after each training it should be better. It should learn new behavior of the user, learn new trends of the items. So that's a thing. And one quick point that I should mention is that the reason that neural networks are really fancy these days because they're really good for fine-tuning. You have a basic model, you have more data, new data, and maybe these kinds of data are some data, some distribution of data has been changed, and you need to teach your model to learn new patterns. So fine-tuning is a good technique. You cannot do that with for example for KNN or something just like that, or any classical machine learning method. So you need something that you can fine-tune it and make it better, or add some additional layers or classification header or some headers to make it more robust to new kinds of data, and data drift or these kinds of topics maybe happened. And at the end, you need to evaluate your model. So there are two types of evaluation. If you just think of it as a machine learning engineer, maybe you could say that, okay, there are some topics like precision for classification problem, or recall, or area under curve, and these kinds of problems that can help you to assess your model. But on the business side, remember, at the first thing, the problem was that the first step was to define the problem and objective. So your evaluation should be based on that objective. We call those kinds of objective the online evaluation, online metrics. So previous one were offline evaluation, like precision, recall, and these kinds of stuff. But on the other side, we have online evaluation, which is business metrics. So you compare the watch time that you had before, for example, for a YouTube recommender system, or if you're designing a recommender for example, Airbnb, to show good listing to the users, you can just compare, for example, number of the clicks, or at the high level, you can even compare number of the rentings that maybe had been increased. And at the end, you need to deploy your model, monitor your model, because the behavior of the users may be changed after time. So there's not a fixed solution that works for all of the time. You should have a solution which is dynamic and adapt to new users and new data. And whenever we find those maybe data drift, we teach those kinds of data to the model to adapt itself. And then we should make the model better and better. So it's an iterative process. It's not a fixed process, just like any software engineering project, any software engineering product that you want to deploy and create. That's really important to follow. Okay, let's go over define the problem. The problem should be related to business. We talked about it already. So it leads to online metrics used in evaluation. And mostly these kinds of metrics we are following to increase revenue, for example, increase user satisfaction. In YouTube, for example, it can be increasing watch time. In Instagram, it can be increasing scroll time. Airbnb, more book rate. And in ad click prediction, which I'm going to introduce you a metric called CTR, which is click-through rate, which is number of the impressions that we show to the users and number of the click of those impressions. So the problem here is that at first we have a user. If you want to model that problem, the user is going to ask, based on my preference, show me something that I'm going to enjoy about it. And the ML service have some items there, which is millions of items in real scenario projects. So those items can be video, music, posts, or even have multimodality structure. So we should find out that which one should I get that to the user. And we should focus on that. We have millions of items. We have vast amount of items. So it and users cannot wait for the response. So somehow we should have a filtering method to somehow reduce these millions just in a second, just in a millisecond, to then through the API just get the response back to the user. So it's really important to have a really fast and efficient method to get that to the user. And that's the reason that we have multiple pipeline and multiple level recommender systems. Yeah. Okay, let's continue. And I just talked about we have tons of users. I'm gonna go over and introduce you to some basic architecture here. As there are tons of items, we should find a scalable solution because we cannot compare every item which users have preference for each request, and we cannot do that. So we cannot just, we have tons of features and we have some matrix, maybe have some calculation to find out, okay, between these millions, which one do I like more? So we have a pipeline here, which we can call it at first, maybe a collaborative filtering method can be used here, and then a content-based filtering method can be used. So I'm going to talk about content-based and collaborative filtering as well here. So in collaborative filtering, maybe the intuition is that the idea is that if a user like a video and maybe there's another user which have the same behavior as the previous user, maybe the new user maybe like the other video as well. So we have two different people. Somehow we find that they're really close to each other, and there's a new video that has been seen by a new user, the previous user, and so maybe the new user like that video as well. So that's the basic idea of the collaborative filtering, and the goal in collaborative filtering is that we're gonna reduce tons of items into hundreds of items. So somehow, and it should be done really fast, quick as possible. We have tons of items. We do collaborative filtering, and then we're gonna have hundreds of items, and then we have some other techniques, other models, which somehow sort this hundred of items and rank these items and show that to the user. So in the ranking, the model or the input of the model, it's 100, not million. So we can have, more detailed feature of the users, more information in the ranking system, because somehow we reduce the number of the candidates, reduce the input. So that's a better approach. And one other thing that I should mention here is that let's go, and at the end, all of items are ranked, and we should just sort those items and just return it to the user. I will go over this kinds of architecture, and I'm going to introduce two really good papers about those, but that's the basic idea here. And in content-based filtering, the idea is that, okay, if, for example, as a user, if I like a video and maybe there's another video which is really close to that video, maybe I'll like that video as well. So we're going to compare those two contents, those two videos together, and have some metrics that calculate the closeness of those two items. So on the candidate generation, which we talked already, this part, the first part, we can have some heuristic method and ML-based method. So what do I mean by heuristic method? So maybe, for example, in an Instagram application, in Instagram when you're using that application, you follow a new person. So mostly it's likely that if you follow a new user, maybe you want to see those posts, no matter what the ML system is gonna tell you. So it's really simple rules that if you follow a new person recently, so you want to see from that user for now. So that's really simple and basic algorithms that can help you to fool your candidates. So somehow you have thousands of, you should produce thousands of from million, you should produce 1,000 candidates. Maybe first 200 is just about recent following, or maybe hit post. Maybe, for example, the favorite. I don't know. I like soccer. For example, David Beckham maybe just created a reel or something just like that, and he's popular. Okay, maybe I want to show the system want to show that to you. So because he's popular, and then you just fool your candidate generation. There's some approaches to fool this 1,000 candidates and create those 1,000 or 100 candidates. And then we have some other method as well, which is we call two-tower. And we talked seconds ago about how we can have a collaborative system to produce it. I'm going to go over the two-tower architecture here and how we can leverage that. But we should keep in mind that this two-tower network, these architectures are not really precise. They're just gonna help you that maybe this candidate can be a good candidate, but it's not pretty sure that it's a really good candidate for you until the ranking has been done. That's the reason that ranking is important. So we have some lightweight model with less features that can run really fast, and then we're gonna produce some candidates there. So the goal is to find out the embedding or some meanings about the users and items. So we need to represent the users and items in some manner, in some numbered way, in a numerical way. So one solution to do that is to, for example, there is a good post here on Medium, I want to go over it, is matrix factorization and how we can do that. Suppose we have a user here and an item table here, which is the rating between the user and item. And as you can suppose, this matrix can be sparse because not all the users rate all the items. So it's a really sparse matrix. And this is one bad thing about these kinds of matrix factorization problem. We have a sparse input here. And then our goal is to produce two matrices, which with those matrices we can represent user and item. So, for example, this matrix is 4 by 4, and the user matrix dimension is 4 by 2, and the item matrix dimension is 2 by 4. And this 2, which is we call it here the number of dimension, can be whatever you like. So if you increase this number, for example, from 2 to 100 or 1,000, so you have a bigger matrix and you can have more, you can include more information, but you need good data to train those models and find those embedding as well. So the problem is that what are two matrices, which we call user and item, which when they multiply with each other, they can produce a rating matrix. So that's the problem that we should solve here. And there's some techniques that we can solve this. I'm gonna go it really quickly. You can follow it if you like. First is use SVD, singular value decomposition. The other is use stochastic gradient descent, and act it as like a learning algorithm. And the loss function here is actually the rating and subtracted by the embedding of the user multiplied by the embedding of the, it's a dot product here of the item, and then squared error, and that's the way it's gonna be done. And then there's another approach which is called walls, which we can fix one embedding, which is you, and optimize the other one, which is the item, and then fix another one, and then optimize the first one, and repeat this approach until we reach to a point that the loss function is acceptable. So the output of this matrix factorization, is some with those d dimension. For example, d here is d1 and d2. It's 2. Here we have 2 dimension. Somehow we can plot that. So our goal is that this plot and this representation be meaningful to us. So what do I mean by that? I mean that, okay, maybe we have a dimension called D1, which if it's positive, it means it's a male, and if it's negative, it's a female. So somehow actually woman and queen are gonna be on the left side, and maybe man and king can be on the right side. Or we have another dimension which can represent maybe if it's general thing like man and woman, or it's more specific thing like king and queen, which will be negative. So that's our goal, just picture this in multi-dimensional way that you can represent each text or input or whatever into some dimensions, which those dimensions can be meaningful. That's our goal. That's the main idea behind embedding. And whenever you see some embedding, that's the main idea. And when we have those embeddings, so there's a really simple approach to follow, is that, okay, I want to find the nearest items between those. Maybe if I have an embedding for example, some video or user, if I find items or users which are really close, and this closeness have some definition, you can understand that, okay, there are some points that are close to each other. And for example, here, if I want to find what are four close items in this plot for the green central point, this can be these 4 items here which are in this circle. But how we can efficiently find that? One way is to compare each point to the green point, but that's a lot. The computation here, it's gonna be the big O of n times d, which that's if you want to find those based on if d is the number of dimension and if number of the points, you should do for example, if you want to do the cosine dot product, you should multiply each dimension by itself, and the computation is too high, especially if the d is really too high, which we need that to capture the meaning. So it's somehow n times n to the power of 2, which is not a scalable solution for us. And that's the reason that there are some algorithms which we call the categorical kind of approximate nearest problem, A and N. For example, FAIS, FAISS algorithm, it's an algorithm that Meta had been developed at. It's called Facebook AI Similarity Search. And by doing some techniques, it can reduce the dimension. So here you have the algorithm here, the time complexity is n times d. So if we somehow reduce the n or d here but meanwhile keep some information there, keep the meaningful information there, for example, by reducing d, so we can achieve a better efficient, better algorithm. So before that, let's talk about how we can find the distance between 2 points. For example, we have maybe a vector called A, which has 3 dimensions, A1, A2, and A3, and B, which has B1, B2, and B3. The dot product is A1 plus A1 times B1 plus A2, B2, and you can follow that. And so when dot product is bigger, it's for example, it's a big number. It means that those 2 numbers are close to each other, but it's not really precise because it depends on each dimension, and maybe if some dimension are really big but the other one is really small, it's not a good metric to find out the closeness of 2 points. The other approach is called Euclidean distance, which the formulation is as follow, and the other one, which I really like it, is cosine similarity, which we do the dot product between these points, but we divide it by the product of length of each matrix. So somehow we normalize it, and therefore the product for cosine similarity is always between 1 and -1. And if it's 1, it means that it's actually the same. They are really close to each other. But if it's -1, it means that they are in the opposite direction, and that's it. So those are some algorithms to how to find the similarity between 2 points, and then we can talk about Faiz as well. So in those kinds of algorithm, for example, clustering can be used, which can be only search only the relevant clusters. So somehow maybe by these techniques we can reduce the number of points there. Maybe, for example, if we have, these are all the points here, maybe do some clustering and just use a single item as a representative for all of these 4. And somehow we're going to reduce that n here in this algorithm, in this notation. So maybe we can reduce n by techniques like cross clustering, or we can reduce d. For example, we can use some techniques to reduce the dimensionality in our meanings, but keep the meaning as well. So how we can achieve training, how we can achieve that beside matrix factorization? There's another approach which is called two-tower networks that in two-tower networks we have 2 different architecture here, which is the left one is user features, the right one is the item features, and we have 2 separate neural networks. So they are at first they are independent to each other, but when we are calculating the loss function, we are going to just integrate those together. So let's go over how we can deploy these 2-tower architectures in training. Suppose we have a user, we have just a single user, and this user, we know that this user specifically one item, one video, one book, or whatever, but it doesn't like 99 other videos. So we have k samples. The user like one of those samples, but doesn't like k-1 number of them. And we can multiply it by m here, which means m users here. And this is gonna be our training data. And somehow at the end, our training is to somehow predict the positive item here among all of the items. And as you can see, we can use cross entropy between these training data to somehow find the loss function here in our training networks. So as you can see here, I'm going to depict it one more time. We have user feature, item feature, some DNN networks, maybe MLP or something, and then at the end we have k probabilities here, which are the output, and there's a softmax here. These are logits, and then softmax, and then k class probability here. And as you can see here, somehow the final output of this neural networks is not the probability. The probability is just gonna be used in the training. But at the end, we're gonna do, the only thing that is important is these 2 neural networks. So somehow we find a neural network, 2 different ones, that we can turn the item features or user features into some embeddings, that we can compare those embeddings together. That's a really good point here to achieve. So maybe offline, maybe after the training, we're gonna do the same from maybe 2 nights in a row. Just do the inference to capture all those embeddings, and just keep those embeddings in some place that when a user came, we have that plot here that just compare. Previously, offline, we calculated all those embeddings. So right now is the time to just do face or any other algorithm to just find the top K1. Previously, we achieved those embeddings. So that's the point of scalability. We should, prior to calling those API call to find out about the recommendation, we should find the capture of all of the items that we had. Maybe last night we just update that, okay? And we have this dimension. And the other thing is that we should have the user embedding as well. So maybe that user is completely new, maybe it registered right away. Should we train a new model for that, or should we just just call this model during the inference and have some embedding about that user? We have no information about that user. How can we do that? And that's a really good point to focus, because in the user's features in two-tower networks, the feature should be minimized. Maybe we can include male or female. Maybe we can include, because we have no interaction here, maybe we can include we shouldn't include deep information, and all of the things should be previously it should be fixed. It shouldn't be dynamic, because, for example, we cannot include the number of the likes or number of the comments or any dynamic in this step. We're gonna keep those features for the next one, which is the ranking. So the real key point is that the number of the features should be minimum, and really simple features should be included in two-tower architecture. And then because we have those basic features always, we know the nationality, we know the language, we know the English, we know the for example, gender of the user. So we have still some features to use those features, to turn those features into embedding of the user, and find maybe KNN afterwards, and ANN, do some ANN afterwards. So the good point is here that we still have some heuristic algorithm as well. So if the two-tower doesn't work really good at this stage, we still can use the heat or heuristic algorithms to fill those candidates. Remember, here the approach is to fill those candidates, and this is one way to do that. One thing is that here, for training these two types of for training let's go over, make it general. The training and for the validation data and training data, there are some implicit and explicit data which are used for evaluation and training in your machine learning models. So, for example, maybe you can hire some people who can label your data for some classification problem. Maybe if the problem is that, for example, if the post which is you're publishing is the post violent or not, maybe you can hire someone to just label those. But the solution is not scalable. And as I mentioned before, any machine learning model should be scalable. On the training side, you need vast amount of data. Maybe you can keep those high quality data for the validation part, to just validate your approach. But in the training side, you need the signal of the previous users that have been used. So always follow that. For training, for example, maybe implicit feedback of the user or explicit feedback of the user is going to be useful. But for hand labeling, can be used for example, validation. And we can use even self-supervision techniques for the training, which is useful for especially image-based problems. Let's go talk about some feature engineering here. So we can categorize it as numerical data, which can be age, price, watch time, number of likes, which if there's some real linear relationship in the feature, we can use techniques such as scaling and normalization as a score for that. But if it's not linear, for example, we can maybe have some outliers. That's really important. For example, income. It's not really good idea to just use normalization and scaling for income. Maybe it's better to bucketize that and categorize that into some levels. Maybe minimum wage, medium, or average wage, or whatever. And then we have categorical data like country, language, or different classes. So if the number of possibilities is low, we can use one-hot encoding. But if the number of possibilities is high, for example, nationality or country or language, so usually one-hot encoding is not good for that because the number of the features are really too much. And just single or two, one, and then lots of zeros. That's not a good idea. The better approach is to use embedding techniques for that. And for the text data, like comments, info, description, these kinds of data, there are two ways to approach those. The first one is a statistical method, but for example, bag of words or TF-IDF can be used. You can follow those ideas to know more about it. And there's another way to handle that, which we call it, for example, ML method, which we encode the text with already trained model. For example, BERT. BERT is really good for turning text into some meaningful dimension numeric way. And then, for example, we can use even Distill and BERT, which is multilingual and much lighter than BERT. And even we can mix those approaches as well, and maybe use, for example, bag of words at first step, and then vectorize the text, and then use embedding approach to make it more meaningful, and then we can mix this. And for the image, we can use already trained model, which we can turn image into some embedding which are meaningful, and maybe dimension of the closeness of two cats, the score of closeness of two cats are really close to each other. And let's go over the evaluation as well. So for regression task, we are mostly going to use mean squared error, mean absolute error. But for the classification task, there's some metrics here. For example, like recall, true negative rate, precision. And then the really good point here is to pay attention to recall and precision here. And we can have a curve here, for example, in this one. And for different threshold of your classification problem, we're gonna have you're gonna have a plot there, and you can somehow compare two different models with this area under curve for precision and recall and true negative rate. So these are some offline evaluation to do that, and as I mentioned, we have some online evaluation as well. And for the ranking system, we have some other methods to evaluate our machine learning model. For example, the first one is recall at k, which we divide number of the relevant items among top k and divide it by number of all of the relevance, or precision at k, which we're gonna have number of relevant items among top k and divide it by k. And there's some other methods like MMR or DCG, which are really useful, and we can calculate those. So I'm just gonna describe those here really briefly, and you can go and explore the details in mathematic form. But let's go over more ideas, here. Let's talk about ranking models, because until this point, everything was very easy. And the most contribution in recommender system is in the ranking models. The most machine learning techniques that are going to be used and new papers are going to publish is in the ranking based models, not in the collaborative based and candidate generation part. So that's this point and spot that you should shine there and provide different approach there. In ranking models, we try to include deep interaction between features. So previously, we didn't have deep interactions here. In compare with collaborative filtering, we include more features of users and then more dynamic interactions here. So that's the place that we can make our model really smart here, include more features, make it dynamic because we have less candidates, less input, and we can run that. Because we have less inputs, we can scale that solution. We can run all of those 100 candidates in parallel even, and have a ranking score out of it. So there are actually two different methods that are going to be used. I'm going to describe those. One is called deep and wide networks, which is widely used in Google infrastructure. And in deep and wide networks works well if number of features is limited. Like, for example, there's a good paper. We are going to talk about that paper, for example, that this paper implements a recommender system on Google Play Store and, just recommend applications there. There is another paper from Google which is called, and there are lots of papers that you can explore here. I'm just going to talk about these two here. There's another paper called Deep and Cross Networks that works well if number of features is huge and really good for applications. When you have lots of features, for example, in ad prediction, when you should predict, not ad prediction, ad click, predict which ad to show to the user. And at the end, we can treat, let's go over this and talk about this. So these are more references. I'm going to go over these two papers, and then there's a really good book which called Machine Learning System Design Interview by Ali Aminian and Alex Zhu by ByteGo. You can go and study that, and it's a really good point to follow these topics there. So let's talk about this wide and deep learning for recommender system. So it's a paper from 2016. It's about 9 years ago. So let's go over some really interesting ideas here. Memorization of feature interaction through a wide set of cross-product feature transformations are effective and interpretable, while generalization requires more feature engineering effect. So in any recommender system, and remember that all these papers we are going to talk about are focusing on the ranking part, not the candidate generation part. So here is that what's going to tell you is that, in machine learning models, because you have, when you have deep neural networks, you can find the deep interaction between the features. But maybe you miss those simple interactions. Maybe, for example, if a user is maybe if a user is male and the user is less than 18 years old, maybe the user likes to watch Top Gun. So where can you include that in your recommender system? There are really two features that are really related to each other, and they can help you to guess that the user liked that item or not. So these kinds of features, we call it wide features. That we call this, we can include those features in the wide part of the neural network. So by wide, what I mean is that in this picture, as you can see, the recommender system has some deep part and wide part. And these wide parts are just for example, they can be logistic regression that the input is just some, for example, some simple features which have been multiplied by each other, and then a classification problem afterwards. Maybe this neuron here, maybe this input shows that if the user is male and if the user lived in US. Maybe this one shows that if the user is male and if the user lives in US and the user is less than 20 years old. So there are some simple ideas here, and we concatenate these features. Somehow we multiply these features, and then we try to create some, for example, logistic regression here, or some simple models here which are not deep but more wide, to help you to get to the last point, get to the last final result that you want to understand. So let's go over some topics here. But as you can see here, we cannot, for example, let's go over how in this paper we achieved wide networks. So this is the formulation of wide features. This is the formulation of wide features, how we can achieve that. So let's go over it. So this is X, which is the input of that is a vector of D features. And then one of the most important transformation is the cross product transformation. So we're gonna multiply every possible feature that we have. For example, one feature is that the gender is female and the language is English. So remember that this has been applied in App Store, Google App Store recommendation system. And the other one can be female, and maybe the language is French or something just like that. So you should pay attention to these kinds of models here, and so you can follow and read this paper to understand more about it. I just want to give you some ideas. And then there's really another good paper which is called Deep and Cross Network for Ad-Click Prediction. This is by mostly Google engineers and Stanford University. And so the problem for previous model were that in wide and deep model, the problem was that, so if the number of features are high, because somehow we are multiplying and create new features, new cross features here, so it can be exponentially get higher. So, and it's not good. We cannot scale that solution if number of features are too much. This solution is really good for limited features. But if the feature is much higher, for example, which is widely used in ad-click prediction systems, the number of features are high. You just aggregate different types of input and streams from various amounts of sources. So the features are high. You cannot do that and create those features, cross products. So there's another approach to tackle this problem, which we call it deep and cross network. So in deep and cross network, we're gonna have the deep network is the same as before. So as you can see, you can go over it. But the cross network here, somehow, we're gonna multiply the input, which is the features of the item and users that we have. And then we're gonna multiply it by the exact formulation is here. Every time we're gonna multiply features time the product of this layer, and then we're gonna transpose that. And this is really interesting. Somehow because when you multiply these two matrices with each other, which are the same in same dimension, somehow you find the importance of them in respect together. So it's somehow like what happens in query key value in transformer architecture, and so this is what happens there. So you find the importance of transpose of x L by x0, and then we're gonna add some bias and then add it with the input. So the output of this layer gonna be the input of the next layer, and we're gonna do the same. We times it by x0. Somehow we find the importance, and we do it with in this paper the num for L1 times, and then at the end we're gonna concatenate and stack those final logics together and have the final output here. So I just want to mention about, and I don't want to go into the details, go and study these topics, but the main idea is to how we can overcome this vast number of features, how we can reduce those, how we can make it meaningful. And this is one other idea that we can go after, and we should create deep and cross networks, which is widely used here. So thank you so much for listening to me. So in this video, I just tried to introduce you to some topics before getting more, doing more research and these kinds of stuff. So that's just a single step prior to going deep. Thank you so much for listening to me, and I hope, and if you have any question, just reach me out on my LinkedIn. I'm always there and try to help you guys. Thank you so much. Have a good one.